Hello, my name is Sharon, and I'm presenting our research called A Unified Experimental Framework for Comparative Evaluation of Deep Learning Models in COVID-19 Lung Lesion Segmentation. The segmentation of COVID-19 lung lesions remains a challenging task for reliable diagnosis and accurate disease evaluation. We found that most deep learning studies often focus on technical aspects and lack detailed empirical evaluations. A fair assessment of the performance of models from the literature is needed to establish certainty in identifying which model demonstrates consistency. The contribution of this work lies in integrating qualitative evaluation with standard quantitative approaches within a unified experimental environment. The first phase comprises data selection and preprocessing, where we selected public sources of data that have been recognized in the literature as a reference datasets. The datasets are corona cases, MOSMED, and MICAI. Although the evaluated models rely on pre-trained ways, data augmentation techniques through Gaussian blur and median blur were incorporated into cross-dataset evaluation to support generalization. In model evaluation, we selected 5 deep learning architectures: DAPSenet, MISNN, MEDPSEG, MEDSAM, and MEDLSAM, both convolutional neural networks and vision transformers, as the selection of models demonstrated high performance and became prevalent in the literature. The evaluation begins with analysis of quantitative segmentation performance, where we use standardized metrics such as chi-score, intersection over union, pixel-wise precision by applying the Kruskal-Wallis test for statistical significance. Model complexity and efficiency are assessed by evaluating inference time and model size. For the model prediction agreement, we evaluated the consistency between model predictions of different models. In addition, segmentation outputs are analyzed at pixel level by categorizing model behavior as optimistic or pessimistic, where the optimistic scenario corresponds to cases in which the model produces a high number of false positive values, whereas the pessimistic scenario reflects a high number of false negative values. Finally, we apply attention map analysis to provide interpretability of model behavior. The results show that MEDPSEG achieved the highest chi-score values ranging from 0.65 to 0.69 across datasets. This trend persists even after applying data augmentation techniques, reinforcing the observed differences in robustness and generalization. Regarding model complexity, between the model with the highest number of parameters, MEDPSEG, and the model with the lowest number of parameters, MISNN, it was the former that achieved the shortest average inference time. By computing model prediction agreement, we identified 3 clusters of models: a first cluster composed by MEDSAM and MEDLSAM, the second MISNN and MEDPSEG, and the third DAPSenet. For pixel-wise analysis, we found that the most optimistic model tends to double the rate of false positive pixels in CTs. Also, pessimistic models tend to increase false negatives for the negative class at the pixel level by approximately 50%. Also, attention maps results reveal that false positives were predominantly located near anatomical boundaries, while false negative pixels tend to occur in regions with low contralations. In conclusion, this study aimed to showcase the model performance and provide insights into the strengths and challenges faced by deep learning approaches in the segmentation task for future real-case applications. Thank you.